Log on, tune in, find out. Another good idea from Cambridge.
I was a bit stuck with the title for this because I'm going to talk about four different things. So I thought I'd call it Adventures in Emulation, because emulation is the one thing that's going to link these all together. But it's going to be rather diffuse within that general topic. So we'll start off, and I'll talk a bit about emulators. Everyone who's talked about emulators today so far has said that I will explain them. And I don't know whether that's because they didn't want to or because they trust me to do it properly. I suspect the former. And then I'm going to, oops, oh, it doesn't do it. Okay. So let's talk a little bit about emulators. There's been a lot of discussion about emulators, and I'll just recap on the theory for people who haven't got it, because say other people have left me to do that. So we have some simulator, some model here, which is I'm going to regard as a deterministic simulator. I'm going to give the simple version of emulation. There are extensions to emulators which we could talk about for several hours that would enable us to do stochastic models here if we wanted to, but I'm just going to do the simple version. So we're going to treat this as a deterministic black box. So we have some inputs, x, and we have some outputs, y. And for the theory, it doesn't actually matter what this is a simulator of. It could be an aero engine, it could be climate, doesn't really matter. And the basic idea is we treat f as an unknown function. So we're trying to estimate a function given some data, which is the data y, it's a function of x. And we're going to use Bayesian methods to estimate it. Now, if you object to Bayesian methods, and I know some people do, you can redo all this in a frequentist framework. The Bayesian stuff, Michael's laughing, the Bayesian stuff isn't essential. I don't think it makes a lot more sense in the Bayesian ones, but you can do it in a frequentist way, and there's a book by Sattner et al. Where they do that. It works. So we're going to actually model the simulator, this unknown function, with a Gaussian process. And this Gaussian process is just like a Gaussian distribution. If you think of a multivariate Gaussian distribution, and you just let the number of variables go to infinity. So I've got a Gaussian distribution, but on R whatever. So this has a mean, and our mean, we generally put our mean as a set of basis functions, a regression, and these are often, we'll use polynomials here, but they could be anything. They could be spherical harmonics if you want to work on a sphere. They could be Fourier terms if you want to do something that's periodic. Doesn't really matter. Well, it does matter, but it doesn't matter for the theory. We have a variance, which is the variability of our stochastic process, and we have some correlation function that says how a point here relates to a point here. And usually we take that to be a Gaussian covariance function. That gives a very smooth answer, and that's one reason why we do it, in that it guarantees that our Gaussian process has all derivatives. So it's very smooth. You don't have to, there are other forms of this, and if the geostatistics people who are doing spatial statistics will have very much more complex, and they spend a lot of time on those functions. We tend not to. We say our functions are smooth, and if this works, and often it doesn't work, we allow the Gaussian. The reason it doesn't work is that some of the matrices I'll interest in a minute will go singular, and in which case you have to do something a bit clever. So we have a set of parameters, these betas, these regression parameters, the sigma, the variance, and these roughness lengths that we have to estimate. And because it's almost impossible to elicit large covariance matrices, we will assume this is diagonal. So we don't have off-diagonal terms there because it's almost impossible to specify things like that. And because we're being Bayesian, we put a prior on. Well, our prior is that the mean looks like our regressive function. And we have the thing which I've already set up. And you can push that through some Bayesian some mathematics, and you can actually calculate the posterior analytically for a non-informative prior. So you put non-informative priors on, and we can actually get the output. Our emulator has a t distribution, a t to t process, but as n gets large compared to QQ's number of parameters, that will become nice and normal. And this is the expected value at any point, and there's a sort of regression term, and then there's a correction to that that comes from the Gaussian process part, the zero mean Gaussian process part, that bends it to fit the points. So there's the regression term. This matrix A, which is the correlation between all the points, this is where occasionally we get this problem. If two of the points get too close together, then they look the same, and this thing goes singular, and it all blows up. But you can easily solve that. You can either change the covariance function so that two points close together decorrelate faster, or you can take those 2 points and merge them into one using a pivoted Cholesky or some numerical trick. The roughness lengths aren't dealt with in this nice analytical formula, so we have to we estimate those generally by maximizing the marginal likelihood. We can do MCMC and stuff if we really want to. And here's an example. So I'm just going to take 1 plus x plus cos 2x as my nonlinear function. I'm going to take these 4 points, and there's the emulator, and these are the uncertainty bands. Now at the points where I have the data, there is no uncertainty, because I'm building an emulator of the model, not of some sort of reality that has uncertainty attached to it. So here we know exactly what the answer is, so there's no uncertainty, and the uncertainty collapses down. Now there are cases where I wouldn't want to do that, and I put a nugget here, which would be an error term, so these points, this line wouldn't have to go through that point. And one advantage of doing that is it makes everything numerically a lot nicer, because on this matrix here that I said would go badly wrong, the nugget adds a point on the diagonal, so everything becomes invertible and very nice. But there are side effects with nuggets, so I'm not a great nugget fan. I know other people are. Okay, that's the basic emulator theory. Now, I've shown that in 1D. We're doing this in tens of dimensions. Okay, so it's a bit more complicated than the basic theory, but that's the basic theory. And if you want to know some of the extensions, we can talk about it later, or you can look up the Muckham toolkit that Michael gave you the address for earlier, which goes through this in, I was going to say excruciating detail, but it goes through it in great detail. It tells you everything you need to know. So the adventures, what I've been playing with, and the 3 sort of case studies I'm going to talk about. The first one is highly nonlinear models. Can we emulate models which have steps in them? Because one of when I set up that correlation function, it imposed the smoothness, that a point here is correlated to a point here, and if there's a step, then that's not true. So can we actually abuse the method and work with models with steps in particular the Stommel model? And then I'll talk a bit about emulating extremes, and finally about using emulators as parameters within models. So let's look a little bit at the Stommel model, and this came out of a talk that Robin Tuck-Macon, who was here earlier, she went and gave a talk at UEA about some work she was doing emulating the ocean component of a climate model, and one of the questions she was asked, could you do the Stommel model? So she came back and we had to go. So the Stommel model, basically you have 2 boxes, the equator and the pole, and you have temperature and salinity here, and you start off with initial values and set it off. There are actually four parameters in here, but we're only going to use 2 because this is just a didactic example, so we're not emulating this in a serious way. But if you start off with different values of t and s, delta t and s difference, you end up with one of 2 solutions. And if you plot those on a scaled, so this is the salinity difference, this is the temperature difference, and this is the final density difference, and you get this shape here, and you've got one value here and one value there. So that's not the thing you'd expect an emulator to do a good job on. So this is our emulator results. Just pushing it straight through that standard theory. We haven't done anything clever. I'll talk a little bit about what clever things we could do. But here is the actual difference between those two contours. And here's the contour we estimate as the 50% line between our maximum and minimum. And there are 40 points there. We've only put down 40 points. We did an initial experiment, and then we put the rest around here. So we did do a little bit of sequential design, but we haven't cheated and told it where that line is. The main problem with the emulator is that it is, the color here is the variance, and where it's colored, it's where our estimate of the line could be. So this is the variance on the estimate of the contour itself. So this is 2 standard deviations around the contour. So here we are very overconfident. We have too much confidence in where our contour is, whereas here, although we've got it wrong, at least within our confidence limits we have the right answer. So overconfidence is the problem with this emulator, not underconfidence. And the reason we get overconfidence is that as we put points close to the line, we nail down the uncertainty, whereas near that line we actually should be expanding our uncertainty because that's where the step is. So ideally we would redo the theory with a variance that changed across the line, and in fact our sequential design makes this worse, because you could imagine if we did a very sequential design, we could say, well, we'll just put points around here and nail down this contour by putting hem stitching it. But if you did that, you'd keep nailing down the uncertainty, and you make yourself more and more sure where you really want to expand the uncertainty. So yes, we can do a reasonable result, but clearly the smoothness does have effects, and we can work out what those are. So that's the first one. Now I'm going to talk a little bit about extremes. The saying in my institute is that no one was ever drowned by mean sea level. It's extremes that actually affect people's life in the future. The climate impacts are almost all to do with extremes. They're to do with heat waves, they're to do with big storms. Now, there's a whole area of statistics about the statistics of extremes, and this says that if we, like the central limit theorem, there's a thing that if you have a variable, as it gets bigger and bigger, then you just power up this distribution, and you can scale that down, and that goes to a limit. And that limiting distribution is what's called the generalized extreme value distribution, and it looks like this. And we can do that with climate models. We can take weather simulators, we can take regional climate models, and generate simulated future, and we can do the extreme value analysis and produce estimates of extremes. But those estimates, they have the uncertainty that comes from fitting this to the data, but they don't have the uncertainty from our parametric uncertainty in the model, the perturbed physics that we might be interested in. So can we actually emulate extremes across on ensemble climate models in the way that we were emulating means, that Jonty was emulating the climate across North America in the Holocene. Now, we can't use Gaussian processes for this because extremes are very non-Gaussian. They have that generalized extreme value distribution. So what I've been thinking about, and I'm not going to show you the results because I haven't got any, is how we might, as well as using, instead of using Gaussian processes, there are extremal processes, these are called max stable processes. So in the same way as we had that Gaussian process, you can build a stochastic process where all the marginals are extreme value distributions. And the one that's they are much more complex than Gaussian processes, and you have to delve into the probability literature to find these things, and it gets quite hairy mathematically, which is one reason why I don't have results, because I've been reading my way through that literature. The most likely one candidate for building extremal emulators is a thing called the Brown-Resnick process, and that looks like this. So this says that my emulator would be the largest of a Poisson process plus some stochastic process. This could be a Gaussian process, but it doesn't have to be. It could be some other sort of process, and it might be that we want some other process in here rather than a Gaussian process. If you put a Gaussian process here, nothing decorrelates in space. So the extreme here would even affect the stream way over there, regardless of what correlation function you put in it. So there are possibly other processes we'd want to put in there. There is an alternative to that, which is to say that at each point we've got a generalized extreme value distribution that has 3 parameters. Well, why not just put a Gaussian process through all those parameters? And that sounds a good idea, and it was Clive Anderson who suggested it to me that we could do this, and I've been talking to him and to other people about this since. And yes, it is quite nice, but if you do that, it limits the extremal process you get in ways that's it's not obvious. Nothing to do with extremal processes is obvious, but it limits it in ways that are unhelpful. So although this is very attractive, it probably isn't what you want to do. So we probably we'd need to do the Brown-Resnick bit just to prove that this does do what you want to do. This certainly would be easier. So that's about where I've got with extremes, thinking about it. And finally, the other thing I've been thinking about is emulation as parameterization. So we know that GCMs have problems with resolution. You can't resolve what you'd like to. And so that means you have subgrid scale processes. But often we have good process models of what's happening inside those grid cells. But they're too expensive to actually run inside the GCM, which is where you could do it. So the idea is to replace that process model with its emulator. And here's a sort of diagram. This is the GCM, and we have some process model here, and the ones we've been thinking about are models of deep convection in the ocean. So in this cell, we'd have a model which have more levels in the vertical and more levels in the horizontal, and we'd fit that cell in there. And you can run this separately, and we could run occasional runs of that, or we could replace it with its emulator. Now, if we think of the GCM as, again, this little black box which has got some parameters, and it takes the state variable from xt to xt plus 1, and the process model would take those same state variables and give us another state, and it has some parameters of itself, but they also have some nuisance parameters. There are extra parameters. In my deep ocean convection example, there's the vertical structure that I can't get from the GCM, because the vertical structure I want in my process model is more complex. It's much finer. So here I could plug in my process model into the GCM, but I can't do that. So conventionally you parameterize this. We put some simple some parameterization, some bulk formula, and then we plug the bulk formula in. So I'm going to replace that with an emulator. But we have to worry about these nuisance parameters, because my emulator, unlike the bulk formulae are designed to work on the state variables. My emulator needs the full input that I would give the process model. So I have to do something about these nuisance parameters. Now, we might find some of them don't matter during the process when we build the emulator, but we can't rely on that. So we do have to do something about those. And there's two things, well, there's probably more than two. There's two things I thought you can do about that. One is, well, first of all, we encapsulate our prior knowledge about them in some prior distribution, because we're doing some Bayesian statistics, so we have to do that. So we have the probability, some sort of probability distribution about what these nuisance parameters are given the state, because they are state dependent. They're not general, well, they might not be, but most of them will be state dependent. For instance, my vertical structure has to fit in with the vertical structure that I get from the state variables. So there's one way to deal with that would be to say, well, okay, I'll just replace them with the expected value from this prior distribution, in which for my example of the deep convection, I might just linearly interpolate the state variables, and that would give me a deterministic answer, and I can then run my model deterministically in the same way. But that's not terribly realistic. What I could do is now bit this into a stochastic parameterization. So instead of saying I'll linearly interpolate that, I will sample from the possible distribution of the vertical structure that I can get conditional on the points, the state I'm getting from the model. So I can actually make this into a stochastic parameterization, but it's a stochastic parameterization that has included all the physics in the process model. So I'm driving that process model stochastically, but very efficiently, because the emulators run instantly. Even on small laptops, emulators run pretty much instantly. So a summary of that, and again, we're starting to work on this. We've been knocking up some theory of how you will do it, is that emulators can be used to parameterize these subgrid scale processes. They preserve all the physics approximately, because they are approximations, not full models. But if you run the process model many times, we can make those approximations arbitrarily close. We need to get some examples. To say we're actually, Yanis Andrianakis, who works for me, he's busily working out how to run deep ocean convection models at the moment. So something will happen on this in the next few months. And sort of in conclusion, because I'm running out of time, emulators are powerful tools for analyzing climate models. But that's what they are. They are tools for analyzing climate models. They're not ends in themselves. But they're actually, it's not a finished subject. We have this big toolkit that Muckham produced that tells you how to do a lot of this emulation stuff, but there are lots of new exciting applications and places to go that I hope I've shown you some of them, and certainly I'm looking forward to many more adventures with emulators. Thank you.
Do you have any questions? I have seen people use neural networks to estimate radiation increments in GCMs.
Okay. That's a similar idea.
Similar in a way.
I mean, we use neural nets. We use Gaussian processes. You can do this sort of thing with neural nets. The problem with neural nets is you don't tend to get things like the uncertainty estimates out, and they're a bit more black box, so you don't know what's happening inside them. Whereas the emulators we can in fact take apart.
Sure.
Can you just elaborate a little bit on that? So, if I understand what you just said, the neural network cannot be configured to act as an emulator in the way it's defined here.
It can act as an emulator, but if I go back here, I'll go back to my example. Not that one. If I built a neural network and I gave it those 4 points to train it, it would draw a curve that went through those 4 points, but it wouldn't give me those uncertainty estimates, and I wouldn't know what the structure of that curve was. It would be somewhere buried in the black box of the neural network, would be how it did it. The advantage of the way we build emulators is that those regression functions, we know what they are, we control them. The correlation length scales, we know what they are, we control them. The shape of the correlation function, we know and we control it. Neural networks, very good nonlinear fitters, but they are very black box. There are versions of neural nets that are getting closer to this, and Gaussian processes are the limit of a certain form of neural network. So they're not unrelated. But a lot of neural networks, not neural network packages, will do the fitting for you, but they won't give you these uncertainty estimates.
Cecile, did you have?
He just said it.
David, you can have the last word.
Yeah, with emulators.
I get the last
I guess the last one, yeah. Emulators fit in the functions there, so they'd be very good inside the set of points that you've got. How far out can you go from? Obviously, you can do a bit of extrapolation with an emulator, but you can't go too far, right? That'll depend on your roughness length, or something. Or?
Yes. If I extrapolated this out, when I fitted this, there's a mean function is the regression function is a straight line.
Yeah.
If I went out here,
Yeah.
then this would just become a straight line.
Yeah.
Because it just falls back onto the regression
So it's like
function because you've got so far. So there are a certain number of roughness lengths, and that depends on the correlation function, where the data is still bending that straight line. The advantage if you did go right out here is that these uncertainty estimates would have zoomed out here and it would have told you that it wasn't doing a good job. The great advantage of these uncertainty estimates is it does tell you where you can trust it. Now one of the questions is how you validate your emulator. And of course you validate the emulation. You don't just validate the mean, you're validating the mean and the uncertainty. So if you've got, let's say I did go out here and there was a point here, it would say that's okay because it's within the uncertainty band. So you do have to be a little bit careful when you're doing the validation.
Your best estimates to be in the middle of all the points.
Yes, but multi-dimensional space is big. So, yeah. I mean, the rule of thumb is that you need 10 points per dimension. So if you've got 40 dimensions, we need 400 points. You probably need a little bit more than that, but that's the rule of thumb. And there are good theoretical reasons for why you need 10.
Okay, I think we'll reconvene tomorrow at 9:30. Don't miss it. The great Peter Cox. And I mean great in the sense of